One, two. Okay. Yeah. Sorry, my microphone was not working at all. Hopefully now you can hear me and perhaps even see me if you are live on Twitch. So thanks for joining this 30-something episode of Idempotency, the show where we take this exciting database called TigerBeetle and look how it actually is implemented inside. And the reason why we do this is twofold. Well, first of all, TigerBeetle is pretty unusual in its design. It has some kind of like cutting edge implementation features, like, for example, assuming that storage might fail, that disk might return garbage data, or, for example, avoiding memory allocation at runtime. So that is kind of like, useful thing to look at. But what's more importantly, TigerBeetle is actually pretty easy to understand as a code base. I mean, you can like crack open any file and, well, like for the first hour, it would make zero sense to you. But after that, okay, let me make my microphone slightly less loud because I think I'm clipping a bit. Okay, so hopefully you still can hear me all right. Okay, yeah. And the second reason is that like TigerBeetle. Okay, sorry. Like something's wrong with Twitch right now. Am I even like online? Okay. Okay. Yeah. So apparently, yeah, that's like that's like asymmetric connectivity. You can you can see me on Twitch, but I actually cannot see me on Twitch because like connection from Twitch to me is broken, and that is like one of the things we actually like try to deal with at TigerBeetle, like trying to not assume that like network is like perfect symmetric and whatever, but like trying to deal with jitters. Anyway, the second reason why TigerBeetle is exciting database to look at is that it's actually like relatively easy to understand. You can like open a file, and if you know the overall architecture, you could actually just like like go and trace and understand like very precisely, very exactly what is going on. And that's actually was pretty surprising to me. I mean, when I came to work at TigerBeetle like 2 years ago, I had zero idea about how databases work, and now after working with Codebase for some time, I pretty much understand that hey, there is like no magic. You just like go and do this, and that's what I would like to share with you today, and a week ago, and 2 weeks ago, and the next week, and the week after that, and until we went through the entirety of TigerBeetle. Okay. Sorry for being too enthusiastic today. So what are we going to do today is, once again, we are going to dive deep right into the code and see how the thing works. Specifically, we are looking at how the data actually goes from the client request on disk. We covered a lot of background here. We covered our grid, we covered our free set, we covered our on disk structure of LSM tree. And now we are going and see how a particular transfer executes. And the big thing here is that while the bulk of data is on disk, the data on disk is updated only rarely, and the most of processing actually happens using only in-memory data. So effectively, what we are looking right now is the in-memory structures of TigerBeetle. And last week and the week before that, we were looking at the read path. So imagine you're a TigerBeetle, you get a new request from a client. And as usual, because everything is batch, this request isn't a single transfer. This request is a pack of 8,000 transfers, which you need to execute, sequentially, like not at the same time, not parallel, but you have all those 8,000 transfers ahead of time, so you actually could do something fancy, some batching to amortize work. And the first thing we do to amortize work is that we load data from disk concurrently and in parallel. So imagine, how do you how you process a transfer between two accounts? Well, you need to load one account from disk, the second account from disk, then you need to compare their balances, check that there aren't like overflows, underflows, check all the other properties, then you update the accounts, and then you write them to disk, and then you repeat that for the next transfer. But if you have all the 8,000 transfers at the same time, what you actually can do is that you actually can go to disk and prefetch all the 16,000 of accounts which might be relevant for this batch of transfers. And that is exactly the code we looked at so far. We have 8,000 transfers. We go and we fetch for each transfer the both accounts that this transfer might need. This, in the happy case, goes to the cache and finishes immediately, but in the worst case, it goes to disk and needs some asynchronous work to finish. And again, this asynchronous work might actually be pretty complicated because we need to traverse several layers of LSM tree. However, let's start looking at the source code. Dash Grove. Where is this object cache? Yeah. However, after all those lookups finish, we end up with all relevant database objects inside this objects cache in a particular grove. As a reminder, we have two types of objects in our database: accounts and transfers. These objects internally are represented as a bunch of different LSM trees and a bunch of trees related to a single object, is a single type of object, is called grove. So we have accounts grove and we have transfers grove. Okay. So now we are going to look at the write path. So let's open state machine. And let's look at the prefetch. So prefetch was what we were looking last time. We have an input batch of create transfers or create accounts events. And what we should do in the prefetch is that we need to populate objects cache with all the relevant objects. So this is a function which touches LSM tree on disk. That's why it has this callback, which is called when the prefetch is ended. And this is all called from the replica. So in the replica, you see that we first do state machine prefetch, then we do commit dispatch with client replies, then we call, after that another thing is ready, we call, hey, kind of like commit op client replies ready callback. And here somewhere we call commit operation. And this commit operation calls somewhere it should actually call commit. Yeah, it calls state machine commit. So we get here. And this is what we're looking today. So we actually now have to execute the operation. So this is the input is the batch of events we are executing. The output is the output buffer where we will write results of our execution. So for each transfer, if it fails, we will write an error code there. And crucially, this commit function doesn't take a callback because it is fully synchronous, because by this time all the input output has already happened. All the relevant objects are in the objects cache, and we can rely on that. So okay, there is a bunch of different kinds of operations. We'll probably look at some more of them at some point in the future, but for now it kind of like doesn't really matter which specific operation we are looking at, and for this reason we are going to look at create transfers, which is expected to be like the hottest operation of TigerBeetle, which actually, like does transfer of value between accounts. Okay, so again, the actual state machine for create transfers is a little bit complicated because there is, for example, pending posted transfers, like two-phase transfers. Then there are the concept of linked transfers, so that you could treat a bunch of transfers atomically such that they all happen or they all don't happen. But again, this is not why we're here today. So let's like ignore all those cases and look at like the simplest case, like, hey, here is a transfer, how we are going to create it. Again, this all is pretty simple, and most of these things is just error handling, because again, there might be a lot of different errors, and we need to make sure that for every error, the behavior of the system is super deterministic. So, okay, like if the flags are invalid, we say, hey, this is invalid. If the ID is invalid, we say, hey, the ID is invalid. If this is related to two-phase transfers, then we go to the completely different function, which handles that logic. And again, we are ignoring this. Then we check that the credit account and the debit account are valid. Then, and again, for all other fields, we check that they are reasonable. Again, and the list of fields here is basically this. So for every field here, you would expect to see 1 or 2 or 3 ifs here to verify this validity. Finally, yes, this interesting bit for which we have worked for the past 2 episodes. We go into the accounts growth and fetch the 2 accounts. And if they are not there, then we return the corresponding error that, hey, we cannot make this transfer because the account does not exist. So let's look how that is implemented. And again, this is implemented exactly as we expect at this point. We just basically go into the object cache and do a lookup by the key. And again, this is like some of like the suboptimal naming in that object cache is not, strictly speaking, a cache. It is a cache, but it has a guarantee that certain objects are going to be present in this cache if they are exist. Specifically, it guarantees that everything prefetched for this batch is going there. So if we receive null as a result, we know that it is not like, just a cache miss. We know for sure that this actual account does not exist. I am not sure if we will be able to get into this like cache with a stash logic in today's episode, but let's just keep this in mind. And for now, treat object cache as like opaque. Okay, so now that we have the 2 accounts, again, we verify extra invariance. So for our data model, like again, it's kind of like one of the like big design ideas in programming is that you should always handle like multiples. You should never ever like have singletons. You should always have like some kind of like parameter which says, hey, which instance of a problem is this? So for us, TigerBeetle doesn't model a single ledger. It models a bunch of ledgers which are orthogonal to each other. So that's why every account and every transfer is stamped with a ledger field, which is just a code. And we have this constraint that like ledgers are essentially parallel. So we enforce that transfer and account belong to the same ledger. Okay, then I'm actually not sure like why do we need get transfer? It doesn't. Okay, yeah, it kind of like, okay, it's again this like small thing that in these adjustments, like there's like two levels of abstractions. When we are getting accounts, we reach directly in the growth. When we are getting transfer, well, we have this helper function which goes and reaches in vertical growth. And the like surprising thing here is that like, hey, this is like the same operation, but in code we have like two levels of abstractions, which is like less than ideal. But well, nobody's perfect, even TigerBeetle. Although we are pretty close, hopefully. Okay. So again, after we try the count, we also need to verify that, hey, this transfer is unique. So that's why if we like get the transfer, then we again return an error. And okay, interesting. So when what does it mean that like the transfer exists? It means that like the IDs match, but all the other fields might be different. And kind of like if you have any other field different, then that's an error. But if you get like exactly the same transfer, it is kind of like actually idempotent. So this exists here is kind of like sort of like not really an error. It just tells you that, hey, actually this transfer was already processed successfully. And this is kind of like really really important, because like you want to have this idempotency in the end-to-end sense. Like if you submit a transfer from a mobile phone, like there is no way you could make sure that this particular like TCP packet actually gets to the TigerBeetle and this particular instance of the transfer gets processed. So the only like reliable way to do this in the face of unreliable network is that your mobile phone continues to submit in this exact same transfer until it receives a response from the server. And that means that actually the same transfer might be submitted a couple of times, and the second time you will receive that exists code, which you should treat as a successful completion of transfer. And if you receive any other error code, well, that would mean that there is some kind of a logical bug in your application, because it assigned the same ID to logically different transfers. Okay. Anyway, finally we after I don't know how many lines, it was like 100 lines. Well, maybe slightly less. Okay, actually, okay. After 2 kilobytes, after 2 kilobytes of code, we actually get to the actual execution, and the actual execution also starts with the error handling. So we carefully check that nothing would overflow, and there's like a lot of things which could overflow. Then we check the internal oh dear. It seems like we are having an invasion live on Twitch, so I will probably not be able to respond to questions in Twitch. But anyway, so where we are. Yeah, we check that nothing overflows. Then we check the logical invariance that, hey, if your account is such that debits must not exceed credits, and actually this doesn't happen, then return error, etc., etc. So finally, here, we get to the point where we actually go and execute the transfer, meaning that we add it to the debits on one side and to the credits on the other side. Why? Well, because that's double entry counted, because we don't want to like create or destroy money. We always maintain this global balance that across all accounts, sum of debits is equal to the sum of credits. Okay, and after we did this logical operation, we actually go and add this new object in the database. So we say particular growth, like transfers growth insert, or the accounts growth update. And that's basically it. And we repeat this thing for every other transfer. So again, let's look at our growth and, well, our growth, because again, reminder, here we are operating logical objects with accounts and transfers. Internally, those objects are represented as a bunch of different trees, which we will actually see very shortly. But the object which I'm confused, but the dig type which encompasses like the whole bunch of trees related to a single type is called growth. So that's why we call growth insert, and that will actually handle all the trees. And again, this is something which we discussed, I think, 3 episodes ago, like how you actually represent something like this is a bunch of trees. And the idea here was that, well, we have a primary tree, which is called object tree, which is a list of accounts sorted by their timestamp, where a timestamp is internal small id. And then if, for example, we also want to have an ability to look up an account using this ID, alongside this object tree, we store an ID tree, which stores pairs of timestamps and IDs sorted by the ID. So when you want to look up account by the ID, you first do a binary search in this ID tree to locate ID timestamp pair, then you extract timestamp from this, then you do binary search in the object tree for accounts using the timestamp as a key. Okay, perfect. Perfect. Oh, let's just go and look how it works. Okay. We want to insert a new item, a new object into our growth. Well, as usual, if we are running with extra assertions, then we check that insert indeed inserts a new object rather than updates the old one. And this is important for indexes. We'll understand that once we look at the update. So that's why kind of like, in high level APIs like in-memory hash map, you typically have like a single API to insert or update object, because like you kind of like it doesn't really matter what is happening under the hood as long as the new object is in the hash map. But when you actually go to the LSM level, go to the indexes, you need to keep track of those things because those things are different. Okay, perfect. So first of all, we go and insert this thing in the objects cache. And then we need to update each of every tree we have. So we have the objects tree. So object is a tree. Yeah, right. Objects is a tree, IDs is a tree, and indexes is a bunch of trees. So we put our thing into the objects tree. Then for ID tree, as I've said, we put a pair of ID and timestamp. And this is sorted by ID. And then for each of the index trees, we put timestamp and the field. And it's actually kind of like backwards because those things are actually sorted by the value of the field. So again, let's go back to our counts to our transfers to like understand how indexes works. So okay, so like this transfer, we understand that it is physically it is sorted by the timestamp, but we also have an index by ID, so we can do a lookup by ID. And now, what if we want to do an operation which is give me all transfers for account with ID 92? This means that we need to find all transfers where debit account ID is 92. For that, we would have to use the index tree on the debit account. And in that index tree, we store account ID and the transfer timestamp, sort by account ID. So we go into that index tree for the debit account ID field, and we binary search 92 there. And it like this, like the index tree stores pairs. So we will have like something like 92 like 1, 92 10, 92 like I don't know this such number because well there actually are going to be a bunch of accounts, a bunch of transfers with this account ID. So this is account ID. This is transfer timestamp. Okay, so we like go to this tree and we like extract this whole list of pairs. Then we extract the second components from each pair, and then we then we could look at the actual transfer objects using those components, and we'll take a closer look at that workflow once we get to scans. But again, that's in some rather distant future at this point. Okay, so that's basically the inserted here. We take an object and we insert it in a bunch of trees, in the object tree, in the ID tree, and in any of the index trees. Now, okay, let's look at the update, because the update is interesting, and really kind of like the update is the method you need to look at to understand how a relational database works. Because like, you know, I had this like mental gap for a long time, is that I understood like what is, for example, a B tree, or what is, for example, an LSM tree, like a collection which just stores a sorted list of values on disk. But it was like very hard for me to like, you know, mentally map from collection which is sorted by attribute to various like high-level operations like joins, projections, filters that relational model gives me. And the indexes is basically the answer. The idea here is that if you store, like, if you have a sorted collection, then you can create a data structure which allows you to look up an object, a row in your table, using any of the attributes. And that works by storing sorted arrays of indexes. By storing indexes, and index is like also a sorted array, where it stores pairs of the field which you are building an index over, and the like primary key of the object. The field which is like the main data store is sorted by. Okay, so right now we'll go and understand how indexes work. So we want to update an object, and again, this is pretty important. Transfer. When we go to update here, notice that we pass both the old object and the new object rather than just the new object. This is required exactly to be able to maintain the indexes. Okay, so let's see how this all works. Okay, yeah, first of all, again, extra verification. If we are running with extra assertions, then we need to check that the old object indeed matches, like even like not matches like in terms of like, hey, they are like equal values, but matches in terms of like identity, like even the pointers are equal, matches what we have in the cache. Then we, yes, check that the new and the old are distinct objects, but that they still represent the same objects at two physical moments in time, which is kind of like quirky way to assert that by checking that the timestamp are equal. And the key here with the timestamp is the timestamp of the creation. So we actually, I don't think we have like access here to like the logical time when the old object was last changed and when the new object was changed, so this particular time, but we can assert that those two are like logically the same object. Okay, then okay, what do we do this in the assert? Okay, yeah. So I guess, yeah, we also like sanity check that although the objects are different as pointers and they have a timestamp, they have something else different. So the bytes pointed by those pointers are actually different. Then we sanity check that the key of the object, so the timestamp is the same, which I think is tautological to this one, but again, verify. And we finally check that none of the object is a tombstone. What is a tombstone? Well, as a reminder, LSM tree works by layering new data on top of old data. And the first layer where you find the data matching the key is the answer. That means kind of like, tricky to delete things because, well, if you delete things from the latest layer, it might actually resurrect something in the lower layer. So there is the way that deletion works in LSM tree is that you actually implement this as an update. So instead of like actually physically deleting data, you add a tombstone on the latest layer. But for update, we are not deleting an object, we are changing it. So that's why neither of those must be a tombstone. Okay. Now, what are we need to update here? Well, we need to update object tree. And this is where we do this thing. We like go and update the object tree. And we need to update all the indexes because, well, values of fields might have changed and we need to update this. But as this comment says, we don't need to update the ID tree because we assume that IDs are the same. And well, yeah, actually, yeah, we assert that IDs are the same. And the ID tree stores these pairs of ID timestamps. So again, even if we update some other fields of object, the ID tree stays the same. So again, the most interesting part of today's lecture, how we update the index tree. And again, this is kind of like super simple, but once you understand it, that mental gap between a B tree and a fully relational model goes away. So, okay. There is like a little bit of an indirection here. So how we like, okay, high level. So what are we storing in the index trees? In the index trees, we are storing pairs of field value and the timestamp. And I think this derived index is oh yeah, it's actually simpler. So this derived index is essentially looks up a field in an object, so it projects it, and this all comes down to this very horrible metaprogramming where we say that forest is a collection of groves and each grove is created by this super meta program which constructs the index trees. So how do they do this? So we parameterize index tree. Okay. I don't understand this. Metaprogramming is hard, even if it is as easy in Zeek. What is this field? Oh, right. Wait, it's okay. That doesn't. I don't get it. Like somewhere we should be like passing like this field name so that we could do a lookup here. Okay, let's see field name, field type. Okay, what is this index tree helper type? Oh, right. Okay. Yeah. Okay. This is where I was confused. I was under the impression that the index tree type would be parameterized by the name of the field of the object, so it can do a lookup here. That's actually not the case. Index tree type is parameterized only by the type of the field, and this is actually useful because, well, for example, in transfer, you have a debit account ID and credit account ID, and both of those are account IDs. So physically, the representation is going to be the same. And if you had separate tree types to those two indexes, then you would have monomorphization blow up. So instead, you just say, okay, both of those are just indexes by U128. And instead, we deal with field names here. So this index tree field type helper, this is the thing which is parameterized at compile time, of course, by the name of the field. This index is 4. So when we call derived index, we just go to our object and do a field lookup. And then we convert these into integer because all our LSM trees, well, there's like this constraint, like, in general, like the key in LSM tree could be like anything with the comparison operator. But we figured out that for our use case, actually, everything we want to compare always boils down to an integer. So that's why we have this extra meta code to convert from like arbitrary index, arbitrary type of field, which might be, for example, an enum, into just an integer. So okay, this is what we are doing, and yeah, that's what we get. So this is like the value of a field. We are building index 4. Okay, so let's Okay, so let's kind of like do a work example here. So let's say we want to update account 92 balance 10 to account 92 balance 200. So, and we have our account balance index, which stores tuples of, well, let's call it balance accounts, which stores tuples of the balance and then account ID. So before we had like 10, 92, and perhaps before we had like 10, like 1, and also like 10, 100, and then, I don't know, like 200. Oh, let's do this. 3 and 200, like 4, and 200, I don't know. Yeah, 236. So stuff on the left is balances, and stuff on the right is account internal IDs, that is timestamps. And this is before, and we want to update to after. So we want to, let me do this. We want to remove this field. So, okay, let's just remove it here. And then we want to insert 292. So let's insert it. Okay, yeah, that's what we want to do. It's again super simple. We remove the old pair from the index and we insert the new pair from the index. And again, first we actually need to check whether, well, this particular field actually changed, because if it didn't change, then we don't have to update anything here. And if it did change, and okay, hey, this is, well, okay, no, never mind. So this actually makes sense. And the extra, so like essentially what we want to do is that we want to remove the old field and insert the new field. But we also apparently, as I learned from looking at this code, we also have an optimization an optimization such that if the value of index is 0, we don't actually store this. So we kind of like have an invariant that items with 0 are not stored. So that's why we check that, okay, if previous value was not 0, then we need to remove it, because if it was 0, then it wasn't there. And if the new value isn't 0, then we need to put it. But if it is 0, then, well, we don't store it. And if before that there was something on 0, then, well, we would have removed it. Finally, finally we put the object into the object tree. So this is again kind of like the whole trick which makes the relational model work. We can implement index updates by looking at the old value of an object, new value of an object, different the fields, and updating the index according to the diff between objects. Okay. Do I want to cover anything else here? And again, sorry for not addressing questions at the Twitch chat this time, because like with like 500 people there, it's not really really possible. Okay. Where do we go from here? So I think we can look at two different avenues here. One is what we do with the object cache, how object cache absurd works, which we use here and here. Alternatively, we might want to look at how actual tree updates are happening, which are puts here, puts and removes here, and a put here. I guess, yeah. I'm actually not sure which one is the right one, and that's why we look at something completely different. So I said that we have this optimization where we don't store zero index in the database. I want to like briefly motivate why we need to do this. So why might you want to have this optimization? And one example is transfers with a timeout. So like normally, well, two phases transfers with a timeout. Normally, when you submit a transfer to TigerBeetle, it actually gets executed immediately. But there is a feature where you could say, hey, I might want to do a transfer of like 1,000 to this account. So please reserve this amount. But don't actually go and execute this transfer. Rather, wait until I submit a confirmation. And if I submit a confirmation before this timeout, then like actually transfer this reserved sum of the money. And if the transformation doesn't come within this period of time, then, well, unreserve this amount. So we need to have some mechanism to expire transfers with the timeouts. So we need some way to look up transfers which have a certain timeout value and which are close to expiration. But most of the transfers actually have a timeout of 0. And this is exactly the case where we employ this, well, we employ this optimization everywhere, but this is the case where this optimization actually pays off. Because if most of the transfers have 0 timeout, then, well, we don't need to do anything here. We just like skip this whole update, and correspondingly, which is even more important, we don't store those users bytes on disk. Okay, so let's leave object cache for later, and let's look at the put object and remove object of the LSM tree. I guess. So we have put here, and we have a remove. And oh dear, I have. Okay, this is embarrassing. So I have 8 minutes left, and if I start explaining this, then we'll need an hour and 8 minutes, not 8 minutes. So I guess what I'm going to do, I will explain as much as I will fit in the remaining time, and the next time we'll kind of like start with essentially repeating the same thing. Because, well, it's like useful to, like, this is complex stuff, so it's useful to let it run through your brain a couple of times. So, okay, what's the deal with put and remove? Remove is actually very easy, because as I've said, to implement remove, we just do a put with the tombstone. So to remove a value, we create a tombstone for a value. And what is a tombstone? Well, that's okay. Actually, okay. I need to. I can answer this question. So the question is why TigerBeetle relies on timestamp for identity, and I will get back to that in a moment. But for now, let's finish this. So again, to implement remove, we just do a put with the tombstone. And tombstone is something which compares equal to the value, but which just have a tombstone bit set. So do we have some nice implementations of this function? Well, for example, okay, so composite key is the key which we use for indexes. So we have field, we have timestamp, and when we the actual key is just an integer, it should be just an integer. Yeah, it is integer of like this amount of bits, and then we create a key. We just extract the timestamp, and you see that for tombstone bit, we store it as a least significant bit of the timestamp. And we want to make sure, I think, that two values compare equal irrespective of their tombstones. So that's why when we extract a key for comparison from a value, we take this timestamp and then we mask the tombstone bit. So tombstone bit is 1. Well, actually, I lied to you. It is like not the least significant bit. It's like the most significant bit. So tombstone is the most significant bit. Then we invert it. So this is all ones except the most significant one, which is 0. And then we like bitwise end it with a timestamp masking at this bit. So okay, that is where we are in the tree. Yeah, this is how remove works. Super simple. So kind of like to like maybe do a worked example. So in the groove, what was our okay? So we removed removed 1092. So here the value with so kind of like we want to remove like this pair. So first we extract key from this pair. The key is just 10. And then we insert tombstone. So tombstone from key. So we use 10 and or rather or with the highest bit. And actually, why do we? Okay, this is surprising. Why do we even store a field here? I would expect it that this is 0. Why not 0? I'm asking because this is genuinely surprising. Okay, but well, hopefully we'll understand this later. Okay, now back to the question. Why TigerBeetle uses internal IDs which are different from external IDs? And let's talk about IDs again. So open our data model. You can see that in both transfer and account, we have 128-bit ID and U64 timestamp. For transfers are the same. And the thing here is that the ID is what we expose to our users, and the timestamp is internal ID private to the TigerBeetle. I'm not sure why exactly we need this. What would break terribly if we used external IDs instead of internal IDs? But I have to, well, couple of reasons. I'm not sure like which one of them is decided. One is like just the size. So this is 128 bits. This is just 64 bits. So this is twice as low. Why this is important? Because remember, each transfer is exploded into a bunch of indexes, into a bunch of trees. So for transfer, we have object tree, we have ID tree, and then we have index on debit account, index of credit amount, index on pending ID, index on every of the 3 user data's, index of the timeout, index on the ledger, index on the code. I'm not sure if we have index on the flag. So I don't remember how many trees we have or no, but like I don't know, at least like a dozen. Dozen. Well, dozen is 12. At least 10 indexes or like something like that. And remember that each of the index trees stores a value of a field plus a value of ID. So physically, that means that ID gets duplicated for each of the index trees you have. So this is the field which has very large space amplification. If you, for example, add an extra bit to like user data, then, well, that's an extra bit only in the object tree and in the index tree for this user data. But if you add extra bit into your like primary internal ID, that bit gets added to every single index tree. And as we have a bunch of index trees, that is a lot. And that's why we need to keep the ID small. So the next question, okay, if the primary reason is that you want to keep ID small, then why can't you make this public ID just U64? And this gets to the heart of like the whole distributed architecture of this entire thing, because the core question is like how you assign unique IDs. Because, well, like the principal idea for IDs is that they must be distinct for distinct objects. One way you can assign ID is that you could say, hey, there is like a counter, and every time you create an ID, you increment this counter. So all the IDs are different because, well, counter is incremented atomically. But this solution doesn't scale. That means that, like, everyone who needs to create an ID, they need to communicate around this counter, which creates contention, which grinds your system performance to a halt. So you need some way to create IDs without too much coordination. And a good solution here is randomness. You could say, hey, okay, just create the random ID. And the thing here is like, if you create random ID, like you need to be thinking about collisions. Like, what if like two different clients create a random ID and that ID collides? And well, that is the question of like how many bits you assign to your randomness. Because if you assign a lot of random bits, then the probability of collision actually becomes negligible. And here it kind of like seems that U64 is enough bits, because the probability that like a random U64 is equal to like a particular value, for example, that random U64 is equal to 92, is, 2 to the minus 64. It's like infinitely small. Well, it's not like really infinitely small number. What's like this English word here? Infinities. Anyway, so it's kind of like tiny, tiny, tiny thing which will never happen. But then you are hit with a birthday paradox, because again, your task is not to make sure that like no one generates ID which is 1337. Rather, you need to make sure that no two IDs are the same. And if you generate, say, 1 million accounts, then the number of pairs of accounts which might have matching IDs is actually 1 million squared. That actually greatly amplifies the probability that two accounts might collide. And that is why if you just use U64 as account ID, you might see collisions in real life. But if you, again, use 128 for IDs, then you need to create a lot of accounts to get a non-negligible probability of a collision, even if you use even accounting for the update paradox. So okay, I think that is like the main reason. Basically, the internal ID is repeated for every index tree, so it makes sense to keep it small, but we have to keep external ID large so that it could be random. Thus, we need to maintain like our internal ID, which is smaller. And well, our internal ID is basically that increment and counter, except that it also doubles as a timestamp. Because well, we haven't talked about this, but basically our consensus also maintained like logical cluster time, which is guaranteed to be monotonic, but also guaranteed to be pretty close to real time. I guess there are a couple of extra niceties we get out of those extra internal IDs. One is that, well, because ID actually is a timestamp, we get useful information. We know when this particular object got created, which is pretty nifty. And then we get one more extra thing, that it's highly likely that data is spatially local, that, well, temporally local, that transfers created at the same time would, for example, expire roughly at the same time. Or, for example, that like accounts created roughly at the same time would kind of like transact across each other. And with random IDs, you kind of like, you can't translate that temporal locality into a spatial locality because your ID is random. So physically on disk, accounts might be in a completely different parts of LSM tree. But this timestamp is monotonically increasing. So you get nice spatial, you get like this transformation of temporal locality of when the object was created into spatial locality of where the object is stored on disk. Okay. That was like perfect question to kind of like allow me to jump from this uncomfortable task of like quickly explaining something in a very compressed way. So I guess that means that this is it for today. And the next time we will look at, well, we'll probably just go and look at an object cache because I kind of like it's embarrassing for how long have we been like, you know, touching on this object, looking at it externally, but without peering inside. So the next time is going to be exactly at this time at 5 p.m. UTC, live on Twitch next Friday. No, not next Friday, next Thursday. So exactly a week from now. And if you, for some reason, miss it on Twitch, you could always watch the episode in the recording on the YouTube. Okay, that's it for today. And thanks for all 2,000 people who ended up joining the stream, and for every one of 387 people who managed to not only join it at the beginning, well, 384 right now. Sorry, those three folks who left, they don't get this extra thanks for managing to sit until the very end of the episode. Goodbye and see you in a week.